in case anybody comes on, like, after I've said this. But, so I went back and I looked at our schedule, and, it's not that I don't think we can get through everything that would be remaining on the test today. I think we probably could if we pushed ourselves and we went like at a pretty quick, pace today. But I went back and I looked at our schedule for the semester, and we do have some wiggle room. So, rather than push ourselves through it, I was going to push the test back one class. So rather than have the test next Tuesday, we'll have the test next Thursday. So we'll make the test, Thursday, April, I think that would be, no, not a week from today, the 22nd, I think. Let me look at a calendar here. Yeah, so Thursday, April 22nd. So this way, basically the plan is to do Taylor Maclaurin series today, and then next class will kind of basically tie up any loose ends. So that being said, like, next class I'll have the review sheet for the next test. But in the meantime, like, if you come to class next week and you're like, hey, like, can you go over this, example or this homework or anything like that, like, there will be plenty of time in class to do that as well. So rather than kind of just like race through everything today and then review on, this Thursday, we'll finish stuff. I'll answer any questions this Thursday, and then we'll review on Tuesday. So a week from today, and then the test will be next Thursday. That being said, also, I put up all the homeworks for the rest of the semester, right? So we talked last time about how I'm not going to grade homework anymore. I just put the assignment up and the answers for everything we're going to do for the rest of the semester. So all the homeworks are up there. So if you look at the homework, like, I kind of put it in two chunks. Like, one is, one is the remaining series and sequences stuff. And then the other chunk is, I think I put like end of the semester homeworks. So that'll be the stuff that we do after the test. So, cause we're coming up to the end, and there's not much that we're going to do after the test. Some stuff, but we've done the bulk of Calc 2 we've already done. So after this test, so there's this test that's coming up next week, and then the final exam. Some of that stuff will be on the final exam, and I'll give you a better idea of exactly what's on the final exam as we get closer to the final. No problem. Okay, so then today we're going to, or I should say, does anyone have any other questions before we do what we're going to do today? No? Okay. So today we're actually going to do, so it would be our best interest to finish the homework before the exam on the 22nd. So it's in your best interest if you finish the homework, like, through all the series and sequences stuff, right? You don't need to do the stuff that says end of the semester, right? Because I haven't taught that yet. But yeah, all the homeworks through series and sequences. I think last class we did, 11.8? And I put that homework up. Yeah, so last class we did 11.8. I put that homework up. And then if you look at the homework, let me just double check here. It's in this one. I believe, yeah, so there's homework for 11.8, 11.10, which is what we're going to do today, and then 11.9. So there's like one more set of homework for what we're going to do next class. And then after the semester ends, there's basically 4 sections of homework. So that's what we're going to kind of focus on after this. Does that make sense? Okay. Any other questions? No? Okay. So, oops. So this is section 1110, and it is Taylor and Maclaurin series. Okay, so we talked last class about power series. Taylor and Maclaurin series are special power series. So we're going to kind of like build up a little bit where they come from. So suppose f of x, so we have some function, and suppose that we could write this function as a series, right? So say from n equals 0 to infinity of a sub n x minus a to the n, right? So I have some function, and our main goal is going to be, we want to take a function, we want to write it as a series. And so we're going to kind of do this here to try to figure out how to do that. Okay, so what I'm about to do is not, it's kind of deriving for you where these Taylor and Maclaurin series come from. Then we'll talk about the Taylor and Maclaurin series, and then we'll go through a bunch of examples of doing them. So if I have some function, and let's say I can write it as a series, if I begin to write out what this is, right, this is, maybe I'll put on this line. So this is saying f sub x. So if you plugged in n equals 0, you would get a sub 0 x minus a to the 0. If you plug in 1 for n, we would get a sub 1 x minus a to the first, a sub 2 x minus a to the second, a sub 3 x minus a to the third, and so forth, right? Everyone okay with that? Okay, and this first piece here, right, x minus a to the 0, that's just 1. So this whole entire thing is just a sub 0 times 1, or a sub 0, right, if I were to kind of just look at it that way. Okay, so I'm going to take a couple derivatives, right? So this is just, they're just a polynomial, right? It makes taking the derivatives easy. So f, the first derivative, right? A0 is a constant, so it would go to 0. I would have a1 times the derivative of x minus a to the first, so that's just going to be a 1. In the second piece, the 2 would come down, so I had 2a2 x minus a times 1. The next piece, I would have 3a3 x minus a squared times the derivative of stuff inside, which is 1, and so forth. Right? So I've really got a1 plus 2a2 times x minus a plus 3a3 times x minus a squared plus dot, dot, dot. Does that make sense? Or I should say questions about what I did there? Yeah, so all I'm doing is taking the derivative, right? So a0, so you want to remember all the a's are constants. They're just like numbers. So like if this was a 7, right, the derivative of 7 would be 0, it would go away. If you think of this as 7, say, times x minus a, right, this, or 7 times x minus 1, the derivative of that would just be, I'd carry down the 7, but the derivative of x minus 2 is just 1, right? Same thing here. I have a bunch of stuff to a power. So the 2's got to come down in front. This a2 is just like a number. So we get 2 times that number. This stuff to the power minus 1. So x minus a to the first, right? I didn't write the 1, but really that's what's happening. X minus a to the first power times the derivative of the stuff inside, which is 1. Yeah, so all I'm doing is taking the derivative. I'm going to take the second derivative now, right? So I took the derivative once. We're going to take the second derivative. So the second derivative, again, the derivative of a1, it's just a constant. It's going to go away. So we're going to have 2a2 times 1 plus 3a3, the 2 is going to come down. So really, generally, right, if we were taking the derivative, we'd be like, oh, 3 times 2 is 6. I'm going to leave it as 3 times 2 for a minute, kind of to help ourselves out a little bit. So 3 times 2, and then we're going to have a3 times x minus a to the first power times 1. And again, I would keep going, right? And then if I looked at the third derivative, the derivative of 2a2 times 1, that's all just 0 because that's all just one number. The next part, we're going to have 3 times 2a3 times 1 plus ... right? And we could put another term on here if we wanted to, right? Like if we had wanted to at the beginning, I could have made a4 x minus a to the fourth, right? So here, when you took the first derivative, that would have been 4a4 x minus a cubed. Here, that would be 4 times 3 a to the fourth x minus a squared. Oops, not there. I just took that derivative, right? Plus ... That would have been down here. I would have had 4 times 3 a4 x minus a squared. And if I did it down here, I'd have 4 times 3 times 2 a4 x minus a to the first, right? So you could take as many terms as you want. So I know this all seems like a little weird, right? There's a reason I'm doing this, even though right this second you're like, this is odd. We have some generic sum that we're being equal to our function, and now we're just taking derivatives of it. This is kind of weird. So what we're actually going to do is we're actually going to find, we're going to plug in a, and we're going to find f of a of all these things, right? So if I plug in f of a, right? So I'm plugging into this one here. So f of a, if I plug in here, I'm going to get a0. Oops. Plus, we would have a1 times a minus a, plus a2 times a minus a squared, plus a3 times a minus a cubed, plus ... So we really, the f of a is really just turns out to be a sub 0, right? Because all of these pieces, this goes to 0, this goes to 0, this goes to 0, everything else would go to 0. Yeah, and good, yeah, exactly, James. It looks like a factorial with those derivative parts. Hold on to that thought, because it doesn't just look like it, it actually will turn out to be a factorial with them. If I write f prime of a, so the first derivative, that's going to be a1 plus 2a2 times a minus a, plus 3a3 times a minus a squared, plus ... So this just turns out to be a1. If I look at f, the second derivative evaluated at a, it's going to be 2a2 plus 3 times 2, a3 times a minus a to the first, ... So this ends up being 2a2. The third derivative evaluated at a ends up being 3 times 2a3. And all the other pieces will go to 0. So it's just 3 times 2a3. And so what is really happening here, right, is this is really, if you, as James said, it looks like a factorial. So 3 times 2 times 1 is 3 factorial. So this is really just 3 factorial a sub 3. Just like this one here is 2 factorial a sub 2. This, I could write it as 1 factorial a sub 1. And 0 factorial we actually defined to be 1. So this is actually 0 factorial a sub 0. So there's kind of a pattern going on here. When I take the first derivative, it ends up being 1 factorial a sub 1. When I take the second derivative, it's 2 factorial a sub 2. When I take the third derivative, it's 3 factorial a sub 3, right? If I were to keep going, had I done the fourth derivative, right? So remember, you kind of, I guess, you could do Roman numeral. We usually, after 3, we usually don't do the primes. You could also just do, like, the number. So remember, that's the way to write, the shortcut way to write the fourth derivative. It would be 4 factorial a sub 4. So the nth derivative is going to turn out to be f sub n evaluated at a times n factorial. I should put the n factorial first. Oops. So it's n factorial. I should just write it as a sub. I skipped a thing in my notes. So the nth derivative is n factorial a sub n. Okay, so you might go, what does all that mean? I'm going to get to what all this means. But before I get to what all this means, does anybody have any questions on any of the stuff I did? Okay, so, oh yeah, it definitely seems odd. No lie about that. What I'm doing though, right, is I'm actually figuring out the value of a sub n. So I now have a formula here that it has a sub n in it. I could divide both sides by n factorial. So a sub n is going to be the nth derivative. And I technically really should put evaluated at a over n factorial. So I should have had an of a there. Okay, so you might go, well, what does that get you? Okay, great. Okay, so this actually gets us someplace, right? So if you remember what I started with, okay, I started with f of x was equal to the summation n equals 0 to infinity of a sub n times x minus a to the n, right? So I said, you have some function, you can write it as a polynomial, and generically this is what it would look like as a polynomial. But now I know that here is that formula for what a sub n should be, so I could plug that in here. So my function is really the summation n equals 0 to infinity of the nth derivative evaluated at a over n factorial times x minus a to the n. So this is basically the definition of what we call a Taylor series. So Taylor and Maclaurin were two mathematicians. They both independently ended up working on the same information. Taylor worked with a generic A, and Maclaurin worked where A was always equal to 0. So that's the difference between the two. And so if you think about it back when calculus was invented a long, long time ago, we didn't have things like the internet or Zoom. And so you could have two mathematicians who might have been working on the same information and they might not have known it. Or even if they knew it in terms of corresponding with each other, right? Like you're sending a letter, right? And not a letter like we send a letter today, right? You're sending a letter via like stagecoach and horses, and stuff like that to go find somebody else. So, a lot of mathematics, earlier mathematics, you have multiple people who are working on the same thing, right? That's kind of why, like, we have the Leibniz notation to represent a derivative versus, a bunch of different types of notation, because you had a bunch of people who were working on it at the same time. So, these two people, Taylor and Maclaurin, were both working on, if I have a function, how could I represent a function in terms of a series? And so they did like this type of work here, and they came up with this way to represent a function as a series. So let me go to the next page. Okay, so definition here. All right, let f be a function with derivatives for all orders, right? So what we mean by derivatives for all orders means we can find the first derivative, second derivative, third derivative, fourth derivative, fifth derivative, sixth derivative, right? Like I keep going. I could find as many derivatives as I want throughout some interval containing the value A. All right, the Taylor series, and you have to say what's generating the Taylor series. So the Taylor series generated by f at x equals A is the summation n equals 0 to infinity of f of n of A over n factorial times x minus A to the n. Sometimes people use k instead of n, right? It doesn't matter. And if you were to write out the pieces, this is saying it's equal to f of A plus f prime of A times x minus A to the first, plus f double prime of A over 2 factorial x minus A to the second, plus dot, 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 right? So that's kind of what we just found. The Maclaurin series of generated by f, is the summation n equals 0 to infinity of the nth derivative evaluated at 0 over n factorial times x to the n. So this would be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus dot, dot, dot. So i.e. it is the Taylor series with a equals 0. Questions? No. Should we put it into practice some so we can see what's going on here? Okay. So, oops, restart. Yeah, so the way to differentiate between whether it's a Taylor series, yep, I can definitely go back for a second. So the way to determine whether it's a Taylor series or a Maclaurin series is whether A is 0 or not. If A is 0, it's a Maclaurin series. If otherwise, for a Taylor series, we have to tell you what the A value is, right? So, directions for a Maclaurin series might say, hey, find the Maclaurin series, right? Directions for a Taylor series are going to say, find the Taylor series, find the Taylor series centered or generated by f at x equals a. So they're going to have to give you the a value. Other questions? No? Okay. So, find the Taylor series for f of x equals 2 to the x generated or at x or at a, oh my goodness, equals 3. Okay, so we're trying to find a Taylor series. They give us the a value of 3, right? So what we're looking for is our f of x is going to be equal to the summation n equals 0 to infinity of the nth derivative evaluated at a. Our a is 3. Evaluated at 3 over n factorial times x minus 3 to the nth, right? So I took the formula for the Taylor series and I just replaced the a with 3. Does that make sense so far? We're not done. Yes. Okay. So when you're trying to find the Taylor series, what you're really trying to do is you're really trying to figure out what the nth derivative of 3 looks like. Okay. I want to replace this with what it is, right? So, maybe it looks like 3 cubed. Maybe it looks like 3 to the n. I don't know what this looks like. So we have to figure this out. So the way that we figure it out is by taking derivatives. So we're starting with, we were given f of x is equal to 2 to the x. So the first thing I'm going to do is I am going to start to take some derivatives. So f prime of x. So what's the derivative of 2 to the x? Yeah, so 2 to the x ln 2. F double prime of x. So what would f double prime of x be? Like, what happens there? So the natural log of 2, right, is just a constant. So it's like as if there was a 7. So I'm just trying to take the derivative of 2 to the x, right? So we already said the derivative of 2 to the x is 2 to the x ln 2. And then that's all from this part. And then this ln of 2 part, that just has to come along for the ride. So it's times another natural log of 2. So it's going to be 2 to the x ln of 2 squared. Questions? No. Okay, so what do you think then the third derivative is? Yeah, 2 to the x ln of 2 cubed. Yep. So 2 to the x, because the derivative of 2 to the x is 2 to the x ln 2, and then that other ln 2 squared, that just comes along for the ride because it's a constant. So we have 2 to the x ln of 2 cubed. Okay, so when you're doing Taylor and Maclaurin series, you have to take enough derivatives until you figure out what the pattern is. So do we think we know what the pattern is? Do you think you could tell me what the nth derivative would be? Yeah, so if you look here at every single one of these, right, I have a 2 to the x, and then I have some ln's. When I have the first derivative, I have 1 ln of 2. When I took the second derivative, I had 2 ln of 2's. When I took the third derivative, I had 3 ln of 2's. So when I'm taking the nth derivative, it's going to end up being 2 to the x ln of 2 to the n. Does that make sense? And then remember, we're looking for f sub n of 3. So we want f sub n of 3. So that's going to be 2 cubed natural log of 2 raised to the nth power. Or 8 natural log of 2 to the n. So if I come back up here, right, this tells me here, we just found what this is. We found the f sub n of 3, right? So my sum f of x, so f of x, which we said was 2 to the x, is the same as the summation n equals 0 to infinity of 8 ln 2 to the n over n factorial times x minus 3 to the n. And you might go, well, why in the world would you ever want to do that, right? Like 2 to the x is so nice, and now I have this mess of a series. But the thing is that having a series is really helpful sometimes, right? So even though, yeah, the function 2 to the x is just a nice little function, having the series can actually be really, really helpful. Questions?
So would that equation be our final answer?
Yep. Yeah, both of you guys asked the question at the same time. All right, should we try another one? All right, so find the Maclaurin series for 1 over x. I guess I should write f of x equals 1 over x. Oops. Okay, so remember the Maclaurin series, our a value is 0, right? So we're looking for f of x is going to be equal to the summation n equals 0 to infinity of the nth derivative evaluated at 0 over n factorial times x to the n. So again, I'm going to need to take derivatives, right? So f prime of x is going to be, so remember this is x to the negative 1. So what's the derivative of x to the negative 1? Yeah, negative x to the negative 2. What would the second derivative be? Yep. So the power is definitely going to be x to the negative 3. Remember that this has to come down, right? So negative 2 times negative 1, that's going to give us positive 2 x to the negative 3. What would the next derivative be? Okay, yeah, so it would be negative 6x to the negative 4. So I'm just going to write it a little differently. I'm going to write it as negative, but I'm going to write it as 3 times 2x to the negative 4. A lot of times, if you multiply it out and make it into the 6, the 3 times the 2, it's harder to see the pattern. So a lot of times, if you kind of keep having powers going down, it's easier to see the pattern if you don't multiply, if you kind of only put like things together, right? So I'll take care of the negative. I'll keep switching it between negative and positive. But I'm not going to multiply out the 3 times the 2. Okay, so the fourth derivative. The negative 6x to the negative 4 isn't considered wrong. No, that's totally correct. The problem with it is that we're just working on a process to help us figure out the formula. So in the end, all you care about is finding the formula. So it doesn't matter how you write the middle steps. It's just that generally, when you're trying to find the formula, it's easier to figure out what the formula is when you don't multiply everything out. Right? So like for the fourth derivative, negative times negative would give me positive. I'll do that. But then I'm going to write this as 4 times 3 times 2x to the negative 5th. We'll do one more here, and then maybe we'll see if we can figure out what the pattern is. So the fifth derivative would be what? Yeah, negative 5 times 4 times 3 times 2x to the negative 6. Okay, so do we see some things happening here? Okay, right. There's a factorial. So this right here, 5 times 4 times 3 times 2, that's a 5 factorial. 4 times 3 times 2, that's a 4 factorial. 3 times 2, that's a 3 factorial. 2 by itself, that's a 2 factorial, right? We can remember there's a 1 here in front of that, so that would be a 1 factorial. Okay, so that's good. So it looks like my nth derivative has an n factorial in it, right? Because if we look, first derivative, 1 factorial. Second derivative, 2 factorial. Third derivative, 3 factorial. Fourth derivative, 4th factorial. Fifth derivative, 5 factorial. Does that make sense? Yes, no, we're not done with the derivative, but does the fact that it has an n factorial in it, does anyone have questions on that piece? Okay, so let's take care of the negative. So if you notice, right, my answers keep flip-flopping. Negative, positive, negative, positive, negative. The next one would be positive. So we've seen this idea in a series when stuff flip-flops between negative and positive, right? That happens when you have a -1 to some power. So generally, if you're flip-flopping positive, negative, positive, negative, positive, negative, you're going to have -1 to a power. You have to figure out, generally that power is either you have -1 to the nth power or -1 to the n plus first power. There's no like rule to say, oh, it's always n here or always n plus 1. You kind of want to figure it out. So if you look, I want the first derivative, the third derivative, the fifth derivative. I want the odd derivatives to be negative. So when we want the odd derivatives to be negative, we use this one. So this first one tells us that the odd derivatives are negative. If we needed the even derivatives to be negative, we would use the second one. Oh, excuse me. So we're going to have a -1 to the n. Thank you. Okay, so I've taken care of the negative part. I've taken care of the factorial part. And now I have to take care of the x part, right? So we're going to have x to some power. And if you look, when I took the first derivative, it was a -2 power. When I took the second derivative, it was a -3 power. The third derivative, -4. The fourth derivative, -5. The fifth derivative, -6. So the power is negative, and it's always one more than the derivative, right? So I'm going to put negative quantity n plus 1, or you could write it as -n minus 1, as Aiden and Sandra both said at some point. And then we're really looking for the nth derivative evaluated at 0. So this is going to be -1 to the n factorial, x, 0 to the -n plus 1. Oh, I didn't mean to do 0. Right? Because if you do 0, everything turns out to be 0. See, the problem is, I'm going to tell you guys what the problem is. The problem is I was like, oh, I didn't have this one worked out in my notes. And I was like, oh, but this is a good one. We should do this one between the next, like this one and the next example. So we don't have to change anything that we've done so far. We just have to change the problem a tiny little bit. So we're going to find the Taylor series for this function at x equals 1, which means this is going to be the nth derivative at 1. and this is going to be x minus 1 to the n. So this should be a 1. And this should be a 1. Sorry about that. I should learn my lesson by now, right? Never just randomly do problems that I don't have worked out ahead of time. It's never a good idea. Oh yeah, A equals 1. A equals 1. Okay, so when you plug in 1 to any power is just 1, right? So this whole thing is just f sub n of 1 is negative 1 to the n factorial. Because 1 to the minus n, and this should be minus n, I forgot my parentheses there, plus 1. Okay, so what does that mean? That means our function, f of x, is equal to the summation n equals 0 to infinity. Okay, so our derivative we found out was negative 1 to the n factorial. So all I'm doing is subbing in for this part here, right? So I still have to keep the n factorial on the bottom. So all divided by n factorial times x minus 1 to the n. And my n factorials would cancel out. So f of x is the summation n equals 0 to infinity, negative 1 to the n, x minus 1 to the n. Remember, f of x was 1 over x. So you can take 1 over x and you can write it as a series this way. And I should really note that doing what we did last class, right? So here's a series. You can find the interval and the radius of convergence. So this works, but it doesn't work for everything. So using what we did last class, we're not going to go through it, but using what we did last class, the interval of convergence is 0 less than x less than 2. So you can you can represent our function here, f of x, which is 1 over x, with this series, but you can only do it when x is between 0 and 2. Questions? Sure. Is that better? No problem. Other questions? No? Okay. So should we do an actual Maclaurin series one? Since I tried to make this a Maclaurin series and I wasn't. So find the Maclaurin series for f of x equals 5 cosine 2x. Okay, so like I said last time, and then we didn't use it, the Maclaurin series tells us that f of x is equal to the summation n equals 0 to infinity of f, the nth derivative evaluated at 0 over n factorial times x to the n. So we're going to find the derivative of this. So so our original function, f of x, 5 cosine 2x. The first derivative. So what's the derivative of 5 cosine 2x? Almost. So remember, you're not integrating it. So the integral of cosine of 2x would be sine of 2x over 2. You're taking the derivative, right? So the 5 comes along for the ride. The derivative of cosine, right, is negative sine. So it's going to be minus sine of 2x times the derivative of the stuff inside, so times 2. So I'm going to clean this up a little bit. So it's minus 5 times 2 sine of 2x. Yeah, once we get into integrals, people always want to integrate when you should be taking a derivative. So no worries. Okay, what's the second derivative? Yeah. So we're going to leave the negative and the 5 out in front. We had this 1, 2, right? Now if I take the derivative, and that's all just a constant, so it's all just coming along for the ride. So if I take the derivative of the sine of 2x, the derivative of sine is going to be cosine of 2x times the derivative of 2x, which is 2. So I'm going to group the 2's together. So this is going to be negative 5 times 2 squared cosine of 2x. What about the third derivative? So it's the same type of deal. Yeah. So, right. So we're going to have the derivative of cosine is negative sine of 2x. So the negative 5 times 2 squared hangs around. The derivative of cosine is going to be minus sine of 2x times the derivative of 2x, which is 2. So this is going to end up being, so I have a negative and a negative, so I'm going to end up with a positive. So positive 5 times 2 cubed sine of 2x. We're going to do a couple more derivatives here as well. So let's look at the fourth derivative. So the derivative of sine is cosine, right? So this one would end up being 5 times 2 to the 4th cosine of 2x. And if you looked at the fifth derivative, we'd be back to negative again. So negative 5 times 2 to the 5th sine of 2x. And we're going to do one more, the sixth derivative. So that's going to be negative 5 times 2 to the 6th cosine of 2x. Right? And I just didn't do those middle steps where I kind of wrote down the derivative part. And I'm going to move this up here, whoops, a little bit. Okay, so any questions about the derivative so far? No. Okay, so some things here are easy to figure out what's going on, right? Yeah, so the thing is like you can see the 5 is in everything. You can see the negative like 1 to the n is and stuff. You can see the 2 to the n, but then you have this weird, like it keeps flip-flopping and going between sines and cosines, and how do you write that? So sometimes it's actually easier to figure out what the pattern is if you actually plug in the value we're looking for. So we're looking for the derivative evaluated at 0. So let's actually look at what all of these are if I plug 0 in, right? So if I figure out f of 0, that's going to be 5 cosine of 2 times 0. So you're going to end up with the cosine of 0, and the cosine of 0 is 1. So this first one is just going to give us 5. If you look at f prime of 0, that's going to be negative 5 times 2 sine of 2 times 0. So that's going to be negative 5 times 2 times 0, or the whole thing is going to be 0. If you plug in the second derivative, so f double prime of 0, we're going to get here 5, so negative 5 times 2 squared times the cosine of 0. So we're going to have negative 5 times 2 squared. If you plug in the third derivative, evaluate at 0, you're going to have 5 times 2 cubed times the sine of 0. So that's going to be 0. The fourth derivative is going to be 5 times 2 to the fourth times the cosine of 0. So that's just going to be 5 times 2 to the fourth. The fifth derivative evaluated at 0 is going to be negative 5 times 2 to the fifth times the sine of 0. So that's going to be 0. And the sixth derivative evaluated at 0 is going to be negative 5 times 2 to the sixth times the cosine of 0, which is going to be 1. So negative 5 times 2 to the sixth. So every other piece is 0, right? So I have something, then the next piece would be 0. Then I have something, then the next piece is 0. Then I have something, then the next piece is 0. Then I have something, then the next piece is 0, right? And that pattern would continue. So remember when I first put these up, when we first talked about Taylor and Maclaurin, I actually also wrote out some of the terms, right? I said, oh, this is f of 0 plus f prime of 0 times x plus f double prime of 0 times x over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed, and so forth. Right? If you write out each of the pieces of that series. So what that means here is that my function, which is f of x, right? So our f of x, which was 5 cosine of 2x, it's going to be f of 0, which is 5, right? F of 0, which is 5, plus f prime of 0 times x. So that's going to be 0 times x, plus f double prime, so negative 5 times 2 squared over 2 factorial times x squared, plus the next piece would be 0, right? Because you're going to get a bunch of stuff and it all ends up being 0. Plus, the next piece is going to be 5 times 2 to the 4th over 4 factorial x to the 4th plus 0 plus, I'm going to move this sideways a tiny bit here, and I'm going to move it up so that we got some room here to work with. Negative 5 times 2 to the 6th over 6 factorial x to the 6th plus dot, dot, dot. Right, so all I did was plug in this, this part here is f double prime of 0 over 2 factorial x squared. This term here, which I have just written as 0, it's f triple prime of 0 times x cubed over 3 factorial. But remember, f triple prime of 0 was 0, so that's why it went to 0. So all I've done is kind of write out the terms of this series. Okay, so technically that's an answer, right? Technically we did what we set out to do. However, it's not a nice answer, and I would like to write it as a much nicer answer. I'd like to write it as a sum, right? And so far, it's kind of hard to write it as a sum because I have all those 0 pieces. So in this case, we can ignore all the pieces that are 0. So really I have 5 minus 5 times 2 squared over 2 factorial x squared plus 5 times 2 to the 4th over 4 factorial x to the 4th minus 5 times 2 to the 6th over 6 factorial x to the 6th. And you could theoretically, you could keep going, right? So like, it's kind of a little easy to see the pattern, right? So the next piece would be plus 5 times 2 to the 8th over 8 factorial x to the 8th. Right, minus dot, 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 and we would keep going. So that gives me some hope that I can write this as a sum. So I really want to write this as a summation n equals 0 to infinity of something. And so this one is not as straightforward as just plugging f sub n into the formula, right? So in this one, you kind of want to think about this first piece is what I want to be my n equals 0 term. I want this to end up being n equals 1. I want this to end up being n equals 2. I want this to end up being n equals 3, n equals 4, and so forth. So, if we kind of look at this, right, we use kind of what we've been doing. So every single one of these pieces has a 5, right? So we're going to have a 5. Robert says it looks like 2n. Yeah, it does, right? If you look here, I have a power of 2, a power of 2, and a factorial of 2. Well, that's really 2 times 1. Here I have 4, 4, 4. Well, that's 2 times 2. Here I have 6, 6, 6, so that's 3 times 2, right? Here I have an 8, an 8, and an 8, so that's 2 times 8, or 2 times 4. So the powers on here are 2 n's. So the bottom, so we're going to have times 2 to the 2n over 2n factorial x to the 2n. And then the only other thing we have to take care of is the -1 part, right? So that negative flip-flops, and it's our odd terms that are negative, so we're going to have a -1 to the n. So anytime you do a cosine or a sine, you kind of usually have to work a little bit harder because they do this flip-flopping thing. Questions? Yep, that's the answer. Yeah, that's as far as it'll let me scroll up. So if I'm like down at the bottom, like on the Zoom, you can actually like take all the little people, like the little like, you know, boxes that has me and all the people, and you can actually grab it and move it over to the side if you want. So you can like kind of like reconfigure the way it is. Oh, you need to see what I had up here. Does that help? No problem. Other questions? Yeah, so sometimes writing out the terms helps you figure out the pattern. Yeah. So yeah, Richard, I can go over it again. Are you okay with this part here? Like this first line, how I got this? Okay. And then you're okay that from the first line to the second line, I just got rid of all the zeros. Okay. So now the idea is I want to write it as, in mathematics, we call this a closed form. So what it means is I'm trying to, rather than just have it as this infinite sum looking, I kind of want to be able to write it with the summation. So what I need to do is I need to kind of look at the different pieces of what I have going on. And what I want to think about is kind of what I wrote here in pink. I want to think about this as being the zero term. This is coming from when n is equal to 1. This is going to come from when n is equal to 2, n is equal to 3, n is equal to 4. So I'm somehow trying to relate each of these pieces back to these n values. So the first thing I do is I say, okay, well, every single piece just has 1 5 in it, right? So since every single piece has 1 5 in it, my answer is going to have a 5, right? So kind of like if I were to come over here and rewrite it, what I started with was saying, well, every single thing has a 5. The other, we'll call it quote-unquote low-hanging fruit that you can get is to realize that they're alternating. So it's positive, then it's negative, then it's positive, then it's negative, then it's positive, then it's negative. And it keeps going back and forth like that. So anytime I have that situation, I have a -1 to a power. And I have to figure out what the power is. And so I said before, if all of your odd terms are the ones that are negative, which in my case, that is true, right? It's negative when n equals 1, when n equals 3, when n would equal 5. Then you're dealing with -1 to the n. So that's how I got those first two pieces. Then the next thing I look at is I say, okay, well, I have 2 to some power. Oh, okay, that's good. But I'm still going to go through the rest of it because I bet other people are confused with how I got some of this stuff. So the other thing I noticed is every single piece has a 2 to a power. Now, technically, the first one doesn't have a 2 to the power, but with 0, you usually can get that to kind of drop out. So every single piece here has 2 to a power. So I'm going to need a 2 to the power, and somehow I want to relate, because the powers change, I want to relate the powers to the n value. So if you look here, the power is 2 when n is 1. The power is 4 when n is 2. The power is 6 when n is 3. The power is 8 when n is 4. So each of these powers is just double the n. So that's where I get the 2n from. I'm just doubling the n value to get the power. And then that power is the same power that's on the x. So we'd have x to the 2n. And that power is also the same that's going on in the factorial. So that's how I get the 2n factorial. Other questions? No problem. No? Okay. So that's kind of finding Taylor and Maclaurin series. So in this section, we find the Taylor and Maclaurin series. Next section, like on Thursday, we still have one more thing we're going to do today, but next class on Thursday, we're going to start with a bunch of series where we know this is what the Taylor or the Maclaurin series for them are. And then we're going to use those to actually help us find other series. So that's actually a little bit easier than what this is. But this gives you a little bit of a taste of what to do. The homework for this section, I don't go crazy. I ask you to find 2 Maclaurin series and I ask you to find 2 Taylor series. So it's not actually like too bad. There's not like I'm giving you tons of problems. I'm just asking you to find 2 of each. Okay, so if you remember way back in Calc 1, you should have talked about linearization of functions. And so what linearization of functions does is it takes a curve and it says, hey, if I'm zoomed in really, really close, the curve kind of acts like a straight line, right? Like even if I drew a circle, but if I were to zoom in on this tiny little part of the circle, super, super close, if I did it and I like zoomed in, I could zoom in so much that that little part of a circle would basically be like a line, right? And we represent it with the tangent line. So we use the tangent line to find the linearization. You can use Taylor series to, rather than approximate functions with a line, like linearization, you can approximate functions with a polynomial. So zoomed in, you can approximate a function with a polynomial. Taylor polynomials is the higher order equivalent to linearization. Okay, so what is a Taylor polynomial? So a Taylor polynomial for a function f of x generated by x equals a of order n is, so p sub n of x is equal to f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial x minus a squared plus plus the nth derivative of a over n factorial times x minus a to the n. So while Taylor series is an infinite series, all Taylor polynomial is it's cutting the polynomial off at a certain degree, right? So it's at a certain order. So it could be of order 0, 1, right? So order 0 would just be you're approximating it by the value. Order 1 is what linearization is from Calc 1. And then as soon as you start going up, order 2, order 3, order 4, now you're dealing with higher order polynomials that you can approximate your function with. So it's really no different than what we've been doing, but easier. So it's like way easier than what we were just doing. So for example, think I can fit it. Yeah, I can fit it here. This way we have it. So, for example, find the Taylor polynomials of order, of orders 0, 1, 2, and 3 generated by f of x equals the natural log of 1 plus x at a equals 0. So I am going to need, since I'm trying to find up to, I'm trying to find 4 different things here. I'm trying to find the Taylor polynomial of order 0, the one of order 1, the one of order 2, the one of order 3. And so I am going to need to go up to the third derivative. So we might as well do that first. So f of x is equal to the natural log of 1 plus x. What is the first derivative of that? Or what's the derivative of the natural log of 1 plus x? I know you guys know derivatives. Yeah, 1 over 1 plus x. Okay. And I'm going to move this up here a little bit. So we've got 1 over 1 plus x, or we can think of it to help us taking the derivative x plus 1 plus x to negative 1. So what's the second derivative? It's a negative, right? Because the negative 1 is going to come down, so it's negative 1 times 1 plus x to the negative 2. What about the third derivative? Yeah, 2 times 1 plus x to the negative 3. Okay, so I have all the derivatives. We're going to need to evaluate the derivatives at our a value, so we might as well find that. So we're looking for f of 0. It's going to be the natural log of 1 plus 0, or natural log of 1, which is 0. F prime of 0 is going to be 1 plus 0 to the negative 1, so 1 to the negative 1, which is just 1. F double prime of 0 is going to be negative 1 times 1 plus 0 to the negative 2. So that's just going to turn out to be negative 1. F third derivative evaluated at 0 is going to be 2 times 1 plus 0 to the negative 3. So that's just going to end up being 2, right? Because you have 2 times 1, which is 2. We're okay with that? Okay, so I want to find the Taylor polynomial of all these different orders. I'm going to start with the order 3, the biggest one first, just because I think it's, when you have more terms, it's a little easier the first time you see it to grasp what's going on. So P3 of x, we are going to plug in. So we're looking for f of a, so f of a is 0, plus f prime of a, so that's 1 times x minus a, And RA in this case is a 0. So 1x minus 0. Plus f double prime. So negative 1 over 2 factorial x minus 0. And then plus f triple prime. So it would be 2 over 3 factorial. Oops, this should be x minus 0 squared. X minus 0 cubed. Are we okay with all those pieces? Like where I plug them into? Any questions on any of that? And I'm stopping at the third derivative because I'm looking for order 3. So whatever the order is, that's the derivative you're going up to. So P3 represents the Taylor polynomial. It's just the notation we use, right? Like, so here it's telling you the order. So the polynomial of order 3. So we need to find, that's kind of this n part here. We're going to need to find the polynomial of order 2, of order 1, and of order 0. Yeah, so it represents your highest order, which in terms of the polynomial corresponds to highest power, right? So our highest power is 3. Okay, I'm going to clean this up a little bit. So this is really 0 plus x minus 1. 2 factorial is just 2, so 1/2 x squared plus 2 6 x cubed, or pull this up a little bit. P3 is 0 plus x minus 1/2 x squared. 2 over 6, right, that would reduce to be 1/3 x cubed. So I just basically cleaned up each of my pieces. So if you do in general, you're just finding one of these, right? Like the order 3, or find the Taylor polynomial of order 7. But in our case, we wanted orders 0, 1, 2, and 3. So this is 3, right? Order 2 would stop here. Right? I would take all of these pieces up to here. So order 2, p sub 2 of x, is going to be 0 plus x minus 1/2 x squared. Order 1, p1 of x, is just going to be 0 plus x. And order 0 is just going to be 0. So the idea is these polynomials all represent the function, the natural log of 1 plus x, but they do it at different, to different degrees of success, right? So the natural log of 1 plus x isn't usually going to be 0. It's only 0 when you're close to 0 for x, right? But basically, this is a way that you can approximate the natural log of 1 plus x, just like you did before in Calc 1 in linearizations. Questions? No? Okay, so then why don't we stop there for today? Just like I said before, a quick reminder, I pushed the test one class forward. So the test is no longer a week from today. It will be a week from Thursday. And when we come to class on Thursday, I will finish up the rest of the material. So we'll be doing section 11.9. And then we'll talk about the test. And basically, I will answer any kind of questions you want. And then next Tuesday, we'll review. So again, I'll also bring a review sheet and stuff, or post a review sheet and stuff by next class. And then I think that's pretty much what I was going to say about that. I'll post a review sheet. Next Tuesday will be the review. I'll answer any questions you guys want. And then next Thursday is the test. And then hopefully you guys saw Brian's thing in the chat, but if not, Brian said he's canceling today's SI session, so he'll see everybody on Thursday, or people go to SI on Thursday. Questions? No? All right. Have a good one.